You may proceed.
Good morning. This is Scott Sanford with this week's edition of the SARE Regional Energy Professional Development. This morning we're going to talk about irrigation scheduling with Bill Krantz from University of Nebraska. Last time he talked about irrigation pumping plants. Now we're going to get to the meat of it, which is irrigation scheduling, which is one of the management things we can do to reduce energy use and save water. And there in Nebraska, where Bill is, they know a lot about trying to save water because it's very precious to them. So with that, I'm going to turn it over to Bill and let him proceed. Thank you.
Thanks, Scott. Good morning, everyone. We're going to, as Scott mentioned, we're going to talk about irrigation scheduling this morning. And as time goes through, I'm trying to enter in materials that might be available in different states, and I'm not going to attempt to be all-inclusive on there because basically most every state has some of these components available for people to use as reference material and calculators and the like. But as we get started here, I wanted to make sure that I gave some credit to other people who have put some of this material together. So on the bottom of your screen are other faculty members here at Lincoln that have been involved in developing at least some of the images you're going to see this morning, and have been quite active in our water management team here at the University of Nebraska. In case you want to know what I look like, there I am, the University of Nebraska. Last time, just to kind of get started with the same kind of screen, last time we visited about performance rating of pumping plants. All right, and so we talked about pumping plant performance last time and how much it costs to pump an inch of water, and we'll eventually come back to that whole thing here as we finish up this morning. But the second component of this then is the factors that we can control in the management of the application system, and first being irrigation scheduling, which is for the most part what we're going to talk about this morning, and then water application efficiency is going to be just a small part of it here, but the idea here is we're going to reduce the number of acre inches of water pumped and in terms of trying to do a better job of matching up with crop water needs and utilizing precipitation that's over here on the left to the greatest extent possible. And again, we end up then by summing those up to how much it costs to irrigate a field. The management tools, that we're going to talk about basically allow us to, I've got a repetitive number here, but basically these four questions: when I should start irrigating, when I can stop, how much water does the crop require at different points of the growing season, or how much is it using out of the soil profile, and then have an idea of how much we're actually putting on. So as we look at some of these, then one of the more traditional ways of looking at soil water monitoring and irrigation scheduling involves using the hand feel method, where basically we just take a hand coring device and collect a sample from different depths in the soil profile, this is the widest used method even in Nebraska today because that's what crop consultants typically will do. It's very practical. You don't need a lot of equipment. The one thing about it is probably how accurate can you get, and you really need to be well trained and calibrated with your hand and a lot of experience with different soil textures in order to do a reasonable job with this arrangement. But the answer right there on site. You don't need to necessarily go and consult a table of values for what the current soil water content is. You know it right when you're doing it. It does get to be labor intensive. If you use a soil probe very much, you'll readily know what I'm referring to. But that's really not specialized equipment. And the other thing it does is it allows people to go around the field and get to know the different portions of the field and how they're responding. This is one thing that with the next part here that I'm going to talk about, using monitoring equipment, you don't necessarily get a lot of that in terms of going to different parts of the field. But, you know, basically once we get into the monitoring equipment, and I'll talk a little bit more about these as time goes on this morning, but we get an accurate reading from the soil that we're looking at, and we don't need to calibrate ourselves. We basically know the answer in the field, but we can then work on it in the office or make some calculations outside the field to do that. We don't necessarily need to go out with a soil probe and probe there, and so the low labor requirement is there once the systems are installed. You get readings from the same portion of the field all season long, and these are the kinds of things where you look at trends and how the soil is responding, and then potentially make some adjustments in the way things are going in terms of whether the soil is getting wetter or drier with time. And then typically, you know, you get down to 4 feet. There's not very many people in Nebraska, at least, that will use a soil probe down to 4 feet when they're doing this sort of thing. They generally stop less than that.
We're going to have to...
Anyway, what you're seeing on the screen, at least, would be components of the soil-water balance and where you might get some of those numbers, and we'll talk about this. I apologize for this part. I thought I would be able to transfer this material over the internet or across the telephone line, and it's not working for us this morning. What you're seeing is, and I have the copies of this video available. We put together a video dealing with center pivot management a few years back, and it involves some interviews with some folks in Kansas. What you're seeing to start with here is a guy talking about his use of the Kansas Scheduler program and how easy it is, and that his daughter is a sophomore in high school, and she basically does all the scheduling in terms of doing the math on the computer and feeds the information to her dad that to go out and manage the system, and based on what the CAN-SCHED system is saying, she basically then can help them out. Now, what's on the screen right now, and eventually you'll have available the audio part of this too. This gentleman is a producer in South Central Kansas, about 3,500 acres of irrigated cropland, and what he's talking about are the times when he feels that he can shut his system off. And he figures that on average about 5 days per year he can shut his system off using irrigation scheduling. And he started off with a system that was developed by the ARS group at Fort Collins, Colorado, and Bushland, Texas, and basically a private entity has taken that up and developed an application that utilizes information from the field and does the irrigation scheduling. He does that in his office kind of thing. And here's the 5 to 10 days of pumping per year that he's talking about. And basically, early on in the growing season, people tend to irrigate maybe sooner than they need to. So he feels that using scheduling allows him to wait until he really needs to start the system up. And then if you have a rainfall event during the growing season, he will potentially allow him to start up a little bit later by knowing what the soil water content is, so he doesn't start up quite so rapidly. The last part you're going to see here is at the tail end of the growing season, and he's referring to the crop coefficient curve you see on the screen. This is basically making sure that you utilize water out of the soil profile. I guess, do we have any questions at this point?
No questions so far. And as you do have questions, type them into the chat pod, and we'll make sure that Bill gets a chance to answer them.
Well, we're repeating the video again. Okay. So water management in general basically uses a water balance, soil water balance kind of things, and what you're seeing on screen is kind of a depiction of the components of a water balance. And we look at water that is moving into the crop root zone and the way that water might move out. And so the text in white, in some cases where there's a high water table, you might get some upward flow, a capillary flow up from the groundwater. That's you've got to have groundwater fairly close to the root zone of the crop for this to be a major factor or a factor at all. But primarily then the additions to water in the balance are going to be irrigation water, and for many of you it's going to be rainfall only as we do this. But if we're talking about irrigation scheduling, obviously we need to look at the addition from that perspective as well. On the movement out, if you don't have a confining layer and a high water table, you can have drainage out of the soil profile during the growing season, particularly early in the growing season when the crop is not utilizing a lot of water. The other thing, we certainly, in terms of rainfall, and this will come back to be a factor as we talk about a little bit the water balance approach. Surface runoff then would be water leaving the field area, not necessarily the soil itself. Soil evaporation loss, there's a range in values that could be potentially up to 30% of the total crop water use is soil evaporation loss, particularly under irrigated conditions, and conditions where we don't have a lot of residue on the surface. And what we're really interested in is the last one here, and that's transpiration of the water that moves through the plant itself. This was supposed to be another video that I'll try to talk you through as we go through this. You know, we look at water application uniformity that we really should be above 90%, and there are different ways of doing the catch can test. This happened to be one from Kansas State, where we've got some printouts, and the first image that you're seeing here is one that has a fairly high coefficient of uniformity, and you're going to see these, if you actually do those, you'll see that there's variation in those numbers over time. And what happens then if you don't have uniform water application, typically, you'll see here in this image coming up, is that areas that don't receive as much water as they should, if you take soil water readings in those areas, you're likely to compensate by irrigating again when you really shouldn't have to, just to get water into that portion of the profile. And so if you have non-uniform, in this case, a CU of 76%, you notice the downward trend. So basically, there's not enough pressure in this system to distribute the water at the far end of the system. And so these are the kinds of things that happen with wear and tear on the pump. The sprinkler packages certainly have a role to play in terms of the overall efficiency and uniformity of water application. And this CPED program was developed by Daryl Heerman with the ARS group, and basically allows you to put in the profile of the soil that the pivot runs over, and then it'll give you a printout that you can put in you have regulators or you don't have regulators on the system, and it'll show you the difference in overall water application trends with that kind of thing. So in here we're looking at the high pressure impact and the effect of spacing between the sprinklers, and we really need to try not to cut corners on this. We have wind out there, which it blows on a daily basis. We're going to get some distortion of the water patterns here, and so the idea is that we put these sprinklers on the system close enough together so that the wind drift effect is not as significant, and that the overall infiltration of water into the profile is relatively uniform. So we've got some spacing recommendations here in this particular portion. If we have them on top of the pipeline, and if you have them on drop tubes, or you're down in the crop canopy even closer to the ground than what I'm showing here in this particular image. And again, the idea is to make sure that we get uniform water distribution. And in some cases, we have maintenance issues and sprinkler package issues that are not, where the system is not put in right. Surprisingly enough, even with color-coded and numbers on the sprinklers, we still have some systems that are, the sprinklers are not put on in the appropriate manner. Again, this is some Kansas State data where the sprinklers in the last couple of spans were put on backwards. And maintenance here, we run into these all the time. I'm sure you've all seen them, geysers out there where the nozzles is actually blown out of the system. If you fly some of these systems where you don't get a whole lot of rainfall, you can see where these issues are quite easily. And now we're seeing a producer actually go out and replace a sprinkler, basically something that he just happens to have around, with the idea that he's going to go back and put the right one in there someday. That someday rarely comes when they put the right one back in there. So it's better to have a supply of nozzles to put back there that are the right ones, and at least make sure that the overall distribution is as uniform as we can make it. These are some images from North Central. We're from North Central Nebraska. So, any questions up to this point?
I see none.
Okay. So let's talk about then getting into kind of the basis for irrigation scheduling. We start to use different terminology for some folks involved in this. One of them is a mass water content, where our water content on a dry soil basis is another way to referring to it. Basically we're talking about the mass of water or the weight of water over the weight of dry soil, and it gives us an idea of how much water might be in that soil profile. And typically, although this information is there in the background, we typically don't use the mass water content very much in scheduling. We're more apt to use the one on the right-hand side of your image, which is the volumetric water content. And here we're looking at the volume of water divided by the bulk volume of soil. And so in this case, you end up with a volume per volume. It can be a percent. It can be inches per inch of soil. It can be inches per foot of soil. I mean, it can be a number of different units that you might see out there. And in this case, we're looking at coming up with a percentage normally of available water that allows us to do the calculations of how much water has actually been removed from the profile. So we look at a few more things here in terms of kind of a typical water release curve from a soil. And on the top, you start on the left-hand side, the top there, there's going to be some water above field capacity that might be in the soil for a period of a few days. And traditionally, in irrigation scheduling, this number or this water has not been accounted for very well. And we're trying to do a little bit better job in Nebraska now. This can take 2 to 3 days for this water to actually drain by gravity from the soil profile and out the bottom. And so it's freer water, easier accessible to the plant. And so we're now at least taking it into account that there may be some use of that water as time goes on during the growing season. The middle part here is what we traditionally look at trying to manage. And the management there, if you look at the numbers that are associated here, field capacity would be, after all the gravitational water has moved out of the soil profile, 2 to 3 days after a rainfall, a big rainfall or an irrigation event. In this particular case, the silt loam soil, that number might be in the mid 30% range, or 0.34 here is a decimal. And the bottom side is the permanent wilting point, at which point the plant will basically die, and putting water back onto it is not going to bring it back to life. Those of you who have been involved in this know that the plant can look like it's dead, and if you give it water, sometimes it'll come back, but permanent wilting means it won't come back anymore. And you see the difference here of about 18% water content, volumetric water content, between the field capacity and the permanent wilting point. There's still a fair amount of water in the silt loam soil below the wilting point, but it's not accessible to us at all in terms of the plant water use. And so we're going to try to manage this available water, and really more specifically, management strategies have been to use the top 50% or only 50% maximum of that amount of water. Work done really early on in the irrigation stage found that you could deplete the soil water content to about 50% without impacting yield. And it really depends upon, I think, what the climatic conditions are in terms of whether 50% is a good number or you should be done watering a little bit sooner than that. To do all of these things, we also need to know how much water is getting out there in the field. And we encourage folks, and I know that you do it in other states as well, to utilize a rain gauge. And it's not a bad idea to have these in a couple places. I know in a field, in a quarter section, we certainly have really intense storms come through here, just like everywhere else, that tend to be isolated and could provide 2 inches of rain on one side of a quarter section, and less than an inch and a half or less than an inch on the other. So from the rainfall point of view, you really need to have a fairly decent rain gauge out there and use it. These are the ones that we use now in our Nebraska rain program, where producers record them and send the information on the internet so others can get an idea of what the rainfall distribution is. On the right, the water meter. We're getting to the point now where water meters are being required by our natural resources districts because of the water supply issues. But regardless of that, you really don't know how much water you're putting on unless you have some way of measuring it. And a water meter that's functioning well and is well maintained is one way to get that number. Periodic numbers with the flow meter and the hours of operation can help get you there, but if you have water table fluctuations, you might find other things going on. So as we look at them trying to get into the season and manage these, the idea is that we start off with a yield versus ET line that traditionally that number, and this really is more yield versus transpiration than ET, but it's a straight line. And if you start with irrigation, you continue to add water, you're going to get an increase in yield that is fairly linear regardless of what crop you look at. And for some of you, quality is going to become an issue, so these sorts of things are also involved in that. Now, when we get involved in the irrigation season, our irrigation systems are not 100% efficient. And so what we may actually have in terms of a yield versus irrigation line may look more like the curve that is now on the right. And the idea of water management is that we're going to try to we're going to get a yield here, but we're going to try to do a better job and improve our water application efficiency, or in essence, improve our water use efficiency by the crop, so that we don't apply any more water to the field than we need to get the crop out. Most states have some means of coming up with estimated crop water use from weather data that's recorded in various locations across the state. The regional climate centers are a clearinghouse for this information, and in Nebraska, this slide happens to be some work that my colleague Watermark has been involved with over the last several years at Clay Center, utilizing the eddy covariance and Bowen ratio type of instrumentation to get a better handle on what the crop water use actually is out there in the field, both during the growing season, and he's also been doing work monitoring the water loss during the off season. But certainly, we need to have some means of coming up with crop water use estimates. As we look at the checkbook scheduling, we've got a large number of these available across the country. Whether, depending on what state you're in, you're going to have access to these kinds of things. And checkbook is just that, where we started off, I mentioned the rainfall and irrigation is considered a deposit, and the crop water use basically, in most cases, is what's been used as a removal of money from the checkbook. Fairly quick and dirty, and you don't necessarily need to be out in the field to utilize this approach. And I just went through we need how much water we're applying. In the case of rainfall, we need to be able to determine how effective that rainfall is. If we're on rolling terrain, we might have some surface runoff, and so if we're utilizing the checkbook approach, then we have to estimate how much of that water got into the soil, and that's where we can start to run into a bit of inaccuracy in this approach. We also need to know how effective our irrigation was and how much water is getting into the soil when we apply water with the center pivot. And so you had water application efficiency involved in all kinds of irrigation systems that we need to estimate. And by and large, then, with the crop water use is also an estimate. It comes from the weather data that we just talked about a few minutes ago. Any questions up to this point?
No questions.
Okay. So to begin with, I talked about the soils information, but there's no question that the web soil survey and some of the online data sets are very, very helpful in terms of getting set up and doing some background calculations and management decisions before you go to the field to put soil water sensors or other things out there, or even doing the soil probe kind of approach. This happens to be a field that you can see over on the left-hand side, maybe on your screen. The acres involved is an important thing in terms of how many acres might be irrigated. Certainly, in this particular case, there's 6.8 acres in the Fillmore silt loam. Doubt whether I would manage the whole system based upon trying to water that particular portion of the field, which happens to be a small portion in the upper, kind of the center top in the image on the right-hand side. But we start to get into the 15 to 20 acres in the soil texture. We really can't necessarily not try to make sure that those types of soil textures are managed properly. These happen to be all silt loams. In some cases, there will be silt and sand in the same field, which makes it more problematic to decide where you might go. And depending on the number of acres, my recommendation kind of goes back and forth between using sand as the sandy area or the silt loam area in fields like that. Online, there's soil texture calculators where you have some idea of what the soil texture might be. You can get the percent sand, silt, and clay, and get the soil texture that you're involved with, and the dots with the silty clay loam or silt loam over on the right-hand side here. Depending on how much clay you actually have in that particular soil, and percent sand, silt, and clay is a good thing to have where we put soil water sensors out there, because in a minute we're going to talk about converting the soil water readings that we get from our soil water sensors to some depth of water that's been removed from the soil profile. As we look at then, what the soil looks like in the hand feel, we're going to go back to this just a little bit. We look at the fine sandy loam soil. You do the hand feel method where you try to create a ball with it in your hand. When that soil is fairly dry is when we're going to have, I think, more issues. But this, in actual situation sandy loam soil should never get this wet, this dry, in terms of the way it would look in your hand. If it is, you've already are experiencing and should see a lot of stress out there in the field. We get to the 50 to 75%. Now we're kind of in the management range that we might want to be in. And again, you've got to have a pretty well calibrated hand to be able to determine whether you're at 50 or at 60 or at 70% of available water here in this case. And when we get to the point where we're in the 75 to 100%, here again, now some of that soil, the smaller soil particles stay on your hand as you release the ball, and it's not always easy to figure out where you are. Crop consultants are, in some cases, quite good at this, and in other cases, probably not. But they're probably going to try to be in this range on the far right one here, in the upper range of the soil water holding capacity most of the time, because their interest is to not cause a yield reduction due to not irrigating enough. And this is where soil water sensors, I think, are very helpful in terms of helping us feel more comfortable about going to soil water contents that might be a little lower than that. In Nebraska, at least, we're going to talk primarily about a granular matrix block that was developed by some folks in California 20 years ago or so. And it's now marketed by the Aerometer company. The top part of this shows you if you order them from Aerometer, you're going to get the soil sensor and with a wire attached and two tabs on the top. These are now looking at somewhere close to $30 a piece, and they are durable enough because of the stainless steel and plastic construction that they can be used over multiple years. And so what we've done in Nebraska is add a piece of PVC pipe to the top, and these are, you can glue these on to the top. You see on the screen there the size of PVC that we're using, whether it be PVC or sheet PVC pipe. Either one will work just fine. You can glue it on, and so it starts to become something that you can install in the spring and pull out in the fall if you want to. Now, typically, we'd also drill a hole just directly above where the soil sensor is inside this tube, so that any water that might get into it will drain out. Just a small little hole. And the reason is that on the top of these Watermark sensors, there actually is a little bit of a hole in the top that allows water to come out the top of the sensor. And if that's in the tube and gradually feeds down in, your soil water readings are going to be wet most of the year, when in fact the soil water content may be drying out. So here's a look at maybe assembling these. We typically are going to want to have a portion of the tube stick out above the ground. In this case, I'm showing the 6 to 8 inches sticking out above the ground. And we want to make sure that no water gets into the top. So in our case, we're utilizing a couple of elbows that are put on the top of these and putting the wire out. And so you cut them to different lengths, and I'll show you the depth that we typically are going to put them in into the soil profile, and we're going to glue these things together. And so then in the fall, we'll be able to come out and pull these out quite easily. Well, in some cases, quite easily. Before we get started at installing these in the field, we've got them constructed and are ready for that. The sensors need to be soaked in water and go on through a couple of wet and dry cycles before they put them in the field. This is to kind of condition the sensor to read properly. If you're having them sitting in a bucket of water, they should read 0 on if you're using a handheld meter. And if they're completely dry, they should read about 199. And we'll get back to that here in just a little bit. Placement out in the field, when we get to that point, these are images of drawings of what our traditional approach had been, utilizing tensiometers or Delmhorst soil blocks before. And you certainly want to get some idea, if you're in a furrow irrigated area, what the soil water content might be at the top and bottom of the field, and also in different sets, so you can plan ahead in terms of when you need to be across the field. In some cases, furrow irrigation, you may have to start irrigating before you really would like to get that done. Center pivots, the normal thing in Nebraska at least, is that we have an access road. In this case, it's coming up from the bottom, the more of the broad box. And the center pivot is going to come around, and if there's opportunities to stop the system, it's going to usually stop on one side or the other of that access road. And so in this case, we've got sensors on either side. The 1 and the 2 here basically tell us when we can start irrigating or when the soil is going to hold the water we're going to apply if the pivot is going in a clockwise direction. And the 3 and 4 over on the right-hand side of the access road provide us with an idea of when we need to be around. And so if we may need to start irrigating a little bit earlier, depending on the flow rate of the system, we may need to start irrigating a little sooner than we would like to make sure that 3 and 4 don't become stressed. If we have 2 crops, we might take a little different approach. If we have a part circle, might do it that way. Now, these are, as I mentioned, the traditional way of looking at these, and for the last 3 or 4 years in Nebraska, this has not been the approach. The soil water installations are functioning well, but they're more expensive than they have been in the past. And so we've gone away from 3 or 4 per field, actually to 1 or 2 per field, depending on whether you've got multiple crops or irrigated sort of situation. And it does present some issues in terms of where we place them in the field, and makes that much more important. And it basically then allows us to monitor one portion of the field and look at trends over time. So where we put them out in the field is as I mentioned, more critical. We want to put them in a representative area of the field. This happens to be a soil survey map, a copy from Pierce County, Nebraska. But in essence, each one of you will be working in areas that have soils that vary in a field site. If you deal with soil mapping units very much, you know that we've got some slope in this field. The E slope here is 11 to 17%, the CSE2 in the kind of the center bottom. We don't want it to be on top of that hill, and we don't. The CO here is essentially a 0 to 1% slope, and there's a waterway down through there. We don't want it to put our sensors in that. We want to go for the main soil texture. In this case, you know, we've got basically the Crofton, I think, soil this is, that we have in the field. And we certainly want them to be easily accessible if we're going to read them and use them for irrigation scheduling. So typically we'll put them on either side of our access road, or we'll use some sort of telemetry to get those readings out to an area that we can access them. Now, this can be also wires that are placed on top of the ground, and we'll see some of this here in just a little bit. Here's a look at a cross-section of a soil profile and the depths that we would normally place them. This happened to be a site where we've installed these sensors kind of in a permanent installation so that the producer can till over the top of these if they're in the tillage mode. But typically we like to have them, and we utilize the reading to represent the soil water content for a 1 foot depth of soil profile. And it doesn't necessarily matter all that much whether you place the top one at 6 inches or at 12. It's still going to be read and utilized as if it were in the middle of a 1 foot zone. And again, what you're seeing on the screen is what we typically have used when we do this. And in this case, we're installing them a little different because it's a permanent installation. But the sensor depths are pretty standard, either at 6, 18, and 30, and 42, or 12, 24, 36, and 48 inches below the soil surface. Our recommendation is that we get these out in the field as soon as we can. The idea is that we want the roots to grow around that sensor rather than prune the roots off as we're putting the sensors in. And so particularly the deeper depths here, and this soil probably has a rooting zone that might be 6 to 12 inches deep here. and so we're placing them in the ground, and we typically will place them in the corn row. Part of this has been tradition because of the potential for cultivating later on, and even today, going through with the sprayer can be a bit of an issue with Roundup Ready corn and all those kind of things. And so we install them early and in the corn row that you're seeing here. In the south central part of the state of Nebraska, the Nebraska Ag Water Management Demonstration Network, basically they take the producer to the field and have them be active in terms of installing these sensors out in the field. In some cases, they're going to determine where they're going to be installed, to a varying degree, we work kind of hand in hand with them on a more or less day-to-day basis, answering questions and that sort of thing. And in particular, that part of Nebraska where Watermark and a few other folks have been involved. But the quicker the producer gets involved in this, the more apt they are to take it on and utilize it after we leave the field out there. So installation is critical with these, as in all the sensors that we're going to talk about today. And you know, the Watermark, if we want to get water moving in and out of that soil block, we need to have a good fit between the soil profile and the sensor itself. And in this case, we want to use an Ag Consultant sampling tube, which are available with the company here. If they were, as far as I know, this is the only place that makes this particular diameter. The Oakfield probe is a larger diameter one, so we typically will use this, and we want to specifically ask for the Ag Consultant sampling tube to put on there. I like to use an 18-inch long sampling tube because it allows me to get a little deeper depth of soil in the tube every time I push the probe into the ground. And it just works a little bit better to get the soil out. Labeling these out in the field is important. Eventually you get to the point where you forget whether you started on the right or started on the left, and so that approach is really not what we're looking for. And so once they're installed in the field, you see here where the number 2 is circled. The idea is to label these. You don't necessarily have to label the 1-foot ones. I believe that this one is labeled, but it's on the other side that you can't see on the one on the right. 1, 2, and 3, and the 4-foot one would be off the screen here. Once we have them installed in the field, we want to try to make sure that no water goes directly down the gap between the tube and the soil. And so we're going to try to tamp or pack some soil around the top of our tube here, and then follow up with a little bit of a mound to, if anything, cause water to drain away from these. Once the water gets into the soil profile down below, it's going to move laterally and equilibrate fairly well there in terms of the movement. And so trying to keep the water from going down the tube itself is pretty important. Here's where we used and put it in a permanent installation, basically just real quick like here, where it can be done to hook on the back of a subsoiling shank and you know, basically pull a piece of PVC through the field and feed the wire through the PVC as you go. Typically, we can put these out in the field, at least the PVC part of it, for about $100. And get them out to some place where we can read them, or you know, then we'll have a connection, and I'll show it here, where we put the connections from the soil water sensors to the wire that goes to the data logging system. In this case, inside of a watertight box, and bury these permanently. And you see the wires that are coming up inside this box to make the connection. Any questions up to this point?
No questions.
Okay. most people now are going to utilizing some sort of monitoring device or data logging system. This particular one is the one that comes from Irrigation, the company that sells the soil matrix sensors. And you can hook 8 soil water sensors up to this, or you can hook 6 of these sensors and 2 water temperature sensors up to one of these. And basically then you can program this data logging system to read as frequently as you want. And when you come to the field and want to know what the reading is right then and there, you push the little green button in the center of the box here, and one by one it'll toggle through the sensors that you have installed that are attached to it. And in the fall, the producer then can download the soil water information utilizing the software that's provided by the company when you purchase the monitoring system. Now, arrangement like this will be somewhere in the $550 to $600 these days for an installation. Typically, this would allow us to monitor soil water content in 2 positions in the field. This works fairly well if the center pivot, in our case, most of the time is split half and half with beans and corn. You can monitor 2 different crops that way, or just 2 different positions fairly close by each other in one field. The other data logging system that is out there for Watermarks was developed quite a few years previous to that by a guy who operates basically out of his garage even today in Oregon. The Hansen data logging system provides some rather unique features to it that the Irrigation does not. On the image on the left, you see the LCD screen that is visible once you take the protective cover off. And again, there's a button in the middle that you push, and if you push that button, you're going to see the soil water content at that particular point in time, plus the last 35 days for that particular installation if it's been in there that long. And so it gives producers some idea of what the trends have been over time and how that particular sensor has responded to water applications during the growing season. The image is actually, I think, in an alfalfa field, but it would work just as well for corn, soybeans, and other crops that you might have in the field. It's a little more difficult to wire these up because the water, you see on the one on the right, the wire comes in and you've got to take another cover off and feed the wires into a wiring harness thing at the bottom, and it's not as easy as it might look. And so they have a special cable for downloading it that you can buy a feature, but basically you download the data utilizing a Microsoft kind of approach that is available in most computers. Here's a little closer up of the wiring of these, and also on the left-hand side you see a little silver port coming out the bottom, and that allows you to access the data and download the data without opening the box up later on, and it's pretty important to request that particular feature on the data logging system. Now, we've also utilized some work that was done by some folks at Washington with the ARS group in Washington, and allows us to develop a chart that you see in this particular thing that we can put in the data logging box. And what it allows us to do then is take the reading that might be on the screen and go across in terms of how much water is in the soil profile, how much has been removed, and we have it color-coded so that we kind of get an idea where we'd like to be in terms of management with our irrigation system. This is quite helpful in terms of doing the mathematics later on. This is a little bit more of a close-up. On the left, you see a chart here for the different soils, and with the different colorations that you might see on the chart. A little bit of text in terms of where we'd like to be and where we'd like to stay away from if we're managing our irrigation system. On the right hand, you see that different soil textures have different amounts of water included in each one of these different depths or different components. And so it really does make a lot of difference whether you're in a sandy soil or a loam as to what some of these readings actually mean. Easy access, this happens to be a data logger that's mounted on a post right on the access road. The producer can drive up on his pickup and push the button and get the readings without ever leaving. So this would be a situation where there's wires that are go out to where the soil water sensors might be, some 50 to 100 feet away from the access road. When we get around to managing, obviously the effective root zone is a big issue. If you have the readings down to 4 feet, it doesn't make a whole lot of sense early in the growing season utilizing the 3rd and 4th foot because there's no root extraction from there. And so to take an average reading for those all 4 feet might not be real effective. Later on in the growing season, as we get closer to tassel emergence, the root zone gets developed down to 3 and 4 feet, and in most of our soils, unless there's some sort of a penetration issue, and we're going to want to then take an average of the top 3 foot of the soil profile when we make those kinds of management decisions. And we, in our publications, and these would be true of other publications from other states as well. But you know, this one was developed by Watermark dealing with the Watermark sensor. And across the bottom here, just to enlarge this a little bit, we have what we refer to as triggers for different soil textures. And you know, basically here we're talking about when we'd like to start irrigating or be irrigating when we have different readings from the soil water sensors, because what we're getting over here on the far left is a soil matrix potential, and we can convert to how much water has been removed from the soil profile in the table, but we want to utilize maybe a little different approach and use some trigger points as to when we want to make sure we're done irrigating out there in the field. If you look at the graphics, you know, for silt loam soil, they might look like this during the growing season. You're going to see these soil water sensors respond to water applications, whether it be rain or irrigation. And in this case, the readings, the higher the reading, the drier the soil is, rather than the reverse. And so it's a little bit of a process to get a little different mindset in terms of what something on the top might mean as opposed to something that might be lower. So in this case, field capacity is going to be somewhere around, I'm going to say 25 to 30 reading on this particular, these sensors. And so we've got situations where we're above field capacity during the growing season due to rainfall or in the short term irrigation that might refill that portion of the profile. There's all sorts of ways in which we can do some calculations based upon the readings in the field. And different states have different kinds of things that they're going to work with from that perspective. So I'd encourage you to look for those, and they're available online, a lot of them. They make converting the readings in the field to actual numbers you can use for management quite easy. As we go along, there are telemetry things coming online that allow people to record soil water sensors out in the field and access them from some distance away. And it depends on the type of sensor you have as to how this might work. We do have a bit of an issue on center pivot irrigated fields in that we want the radio antenna and the transmitter to be above the crop canopy. These are line of sight primarily, and so crop leaves intercept those transmissions, and so if we can't get the antenna above the crop canopy, then we have some telemetry issues. And as you all know, the corn hybrids are now 12 to 13 feet tall in some cases, and you really can't put an antenna above the crop canopy and go over it with a center pivot. You just, unless you have a means of causing the installation with the transmitter to kind of move as the pivot comes by. As I was looking for these, this happens to be the publication that we have available on our water.unl.edu site, and there's a lot more information about these Watermark sensors in terms of installation, preparation, and all the other stuff. There's some short videos there as well. If you go to the Nebraska Ag Water Management Demonstration Network subpage of our overall water.unl.edu website. This one happens to go through, you know, everything you need to know about installing the Watermark sensors. Here's the website with the Nebraska Ag Water Management Demonstration Network, and here is the picture showing Gary Zobek working with some producers out there in the field. Okay, questions up to this point?
I think we still have none. Get your questions onto that chat pod, folks.
Okay, the last thing
just a question, a couple of them. One, the water gauge you showed earlier, what brand is that?
What gauge? I'm not with you. What gauge?
The water rainwater collection?
Oh,
a while ago.
I'm not
Maybe
even,
you can just email
I can't answer your question right now, Scott, in that particular one. I don't have that on the top of my head.
Okay, then the other question I had was, for putting in the Watermark blocks, can you use just a steel rod pounded in the ground versus the probe? Because I know on the Irrigage on their website, they showed just a steel, solid steel rod that they pounded in the ground to make the hole. So I'm just curious if there's advantage of one over the other or disadvantage.
Well, one thing is that when you pound a tube in, or a pipe in, well, a rod in, I guess I should say, you end up compacting the soils more around where this sensor is going to be than you would if you use a soil probe. And if you compact the soil, the water is not going to move in and out of the soil as you would like. So from my perspective, I would prefer to use the soil probe and use a cord to do it, even if it's a piece of pipe that allows the soil to go up inside of it, rather than use a rod to pound down in to get to that depth. I think you're going to find that the movement of water in and out of the soil is going to be much more consistent with what the bulk soil is doing if you do it that way.
Sounds good.
Okay. The last thing I wanted to talk about this morning is an inexpensive way in which people can get access to how much water their crop is using on a day-to-day basis. I mean, we've got some 30 or so weather stations, automatic weather stations spread across the state of Nebraska, but we don't have them everywhere. And so if you happen to be in a state or in an area that may not have automatic weather stations to record and give you estimates of crop water use, an inexpensive way is to utilize the ATMOMETer here that's available from the ETgage company. If you go just type ETgage.com on the web browser, you'll get there. And in this case, we have a hollow tube, the white PVC, with a sight gauge on the side and a Bologna plate on the top. It's a ceramic material that allows water to evaporate off the top of this tube, and basically it siphons water up into it as water evaporates. And it's pretty much a one-way plate, and the water will evaporate off of it, but if it rains, the water is not going to get back into this tube. There are a couple things here. I'm not sure why this came across as black, but the little black box in the middle picture is meant to show a type of cover. They have 3 different covers that you can purchase with these. In Nebraska, all of our weather data and estimated crop water use is based on our alfalfa reference crop. And so we utilize I believe it's the number 54 or something like that, cover on this, because it was developed to mimic the water use for alfalfa. And that's the cover that's on the very top of the Bellani plate and picture E. It's meant to mimic the transpiration of water off through the plant leaves. The other thing you see is they've got a little feature for bird spikes or bird preventers. We want to keep this this cover on the top of this sensor or device free of debris, in particular bird dung and like other things that would prevent water from evaporating freely off the surface. And so, ordinarily speaking, we would not want to put these underneath the center pivot because the water is going to accumulate on the top surface of that evaporative surface, and it's going to alter the evaporation that takes place from the ETgage. If you think about it from a rainfall perspective, typically rainfall events are going to be high humidity and followed by or come with cooler conditions that actually cause evaporation to decrease. If we're irrigating on a 90-degree day, we come across with a center pivot, and for a half an hour we apply water on top of this particular ATMOMETer. We're going to decrease the evaporation loss there, that the plants that are around it are not going to experience the same sort of thing, at least not to the same degree. And so not underneath the irrigated areas unless it's a surface irrigated field. Here, this image shows, again, a publication that SWAT put together dealing with this and the installation and all of that. These are good for an area of approximately 8-mile square around these. So producer doesn't need to have one of these per field. They can basically install one in most cases, and you can utilize that information for a broad brush of area around the field. Here's the water accumulation on the top, and the idea of not putting it on top of or underneath the center pivot. If you put, the other thing is that again, getting back to getting material into the evaporative surface on these, if we have dissolved salts in our irrigation water and we irrigate these, the salts are going to be left behind, and eventually the canvas material is going to be cluttered with the salts that are left behind. So that's the other reason for not putting them underneath the pivot themselves. Installation, we want to make sure that we have full access to wind and sun. And so, you don't want these underneath the tree out beside the house. And we'd like to have the wind go through these or by these just like you're out in the field. The ATMOMETer from the company is 40 inches off the surface of the canopy that it's around. And so to do this right, you see in the upper right-hand picture here, if you were going to put this in a cornfield, that's kind of the way you would do it. You would have to keep moving this up as the season progressed and eventually have a fairly tall post. These can be in the corner and dryland corners of an irrigated field if that's a convenient place to get to them. We want to be able to get to them and read them in the same way every time we go into the field. And the way these work is that the ETgage is going to give us the reference ET just like the weather station data does. And so in order to get the crop water use, we have to multiply by a crop coefficient. And this information is all in that publication. And typically here in Nebraska, we use the same crop coefficients as they use for converting the actual weather data to crop water use for different crops. Now, the publication has this table in it, and basically, if you have one of these, you're meant to be alfalfa, so you can use the number directly to schedule irrigation on alfalfa, and then if you're growing corn, soybeans, or wheat, the crop coefficients that we use at least are in the table, and are based upon the stage of growth. And so one can convert these readings that you get from the ETgage to actual crop water use for other crops, utilizing the one thing. So if we have just an example here, we have corn as 12 leaf stage in the 54 canvas cover for alfalfa. The site tube decreased 1.3 inches over a 7-day period. We want to determine the actual crop water use and get the net irrigation requirement and those kind of things. So the potential ET here is 1.3 inches. From the table, if I could show it again on top of here, basically we're looking at 0.88 from the table. You do the math and it shows you that we really have utilized for that particular 7-day period 1.1 inches of water. And depending upon whether we got rainfall during that period of time or not, we make an adjustment for rainfall. So our gross irrigation now is going to be the water use for the week divided by our application efficiency. That gives us 1.3 inches of water applied. So very simple math to get at our need for what the irrigation amount is going to be. Now, utilizing the irrigation scheduling from the Nebraska Ag Water Management Demonstration Network, they surveyed the people that have been involved over time, and their surveys would suggest that we're getting about 2 inches of water savings per year, because most of these people have some fields that they schedule and some fields that they don't. And they started off with 1,500 acres in 2006, and we're over 500,000 acres last summer, and so involved in that network, and it's a sharing kind of network that allows them to go through some of this. But 2 inches of water, kind of overall average is what you might expect. We look at then the cost here, or the fuel savings part of it. Remember from last week, we have a table like this from one of our publications. If we're at 100% of the performance rating for the pumping plant, and we have 60 psi at the pump outlet, and we're pumping from 150 feet coming from the left, that would say that we should use 2.63 gallons of diesel fuel to pump an acre inch of water. So if we have a full-size center pivot here of 130 acres, that would say that the 2 inches of water savings from irrigation scheduling amounts to 684 gallons of diesel fuel, which at today's prices is a fair amount of cost savings as well. And in most cases, not all cases, these kinds of things can be done without impacting yield at all. It's getting back to what the gentleman from Kansas would say, and that is that there are opportunities to not irrigate during most growing seasons that allow you to save some water if you do a good job of scheduling. So, kind of in summary, then here this morning, we've always recommended people use soil water sensors for irrigation scheduling purposes, and we're getting more so that all the time. We want to be able to do this in a representative area of the field and watch the progression over time. If we can also then get at how much water the crop is using an ETgage, that's typically good for periods of 3 to 7 days. I wouldn't want to do it on a daily basis, just because there's some differential in reading from day to day and that sort of thing. And so 3 to 7 days typically is what we would recommend. In the end, we really are looking at trying to get the most out of the field that we can. And I understand this image came from Southwest Nebraska at some point in time, and so that's why we called the Cornhusker State here.